Alright, okay, in this video I'd like to talk to you a little bit about different shapes of titration curves or pH curves that you'll see when you add either an acid to a base or a base to an acid. In this case I'm showing several titration curves for addition of a base to an acid. So you have a situation where you have your acid that's in your Erlenmeyer flask. Note the high quality of the Erlenmeyer flask. And then coming down into that is your burette that has the base in it. Okay, so here is your acid, here is your base. If it's a strong base, you've got your OH minus ions in there. If it's a strong acid, you've got your H plus ions in there. Okay. And carefully you add this stuff dropwise. Add in the base dropwise. Alright. And as you would expect, you add the base into the acid and the pH goes up, as is shown on this diagram. But note that the increase in the pH is not just a nice straight line. It increases in a very particular shape. Notice the kind of the S shape. Okay, it's not a perfect S, but that's essentially the shape of any titration curve. They all look the same, broadly. So when you have a strong acid, say HCl, in your flask, and you titrate into it a strong base, NaOH, alright? If we assume that we have the same concentrations here, 0.1 molar and 0.1 molar, what we'll find as we add the NaOH into the HCl, we have the neutralization reaction between the two, and the acid in here starts to get used up by the base, and so the pH starts to go up. So you have this general increase in pH, and you'll notice around here the pH increase starts to get faster and faster, and that's because more and more acid is getting used up. There is less and less left to contribute to the pH. And you get an almost vertical line here. So at this point, your pH increases very quickly over a very, very small volume. So if we look at, say, from here to, say, here, we can see that the pH increases quite a small amount over a relatively large volume. When we compare, say, from here and look at the pH, which is about there, to here, okay, that volume is, say, about here, and that pH is there. Over this point, we have over a very small volume, a very high increase in pH. And then when we get to past here, the volume from here, which is approximately there, to about here, rather large volume. Again, you see quite a small increase in pH. So it's right here in the middle where you see that big increase. All right, and there is an important point here right in the middle, particularly for strong acid and base, called the equivalence point. All right, the equivalence point is simply the point in the titration at which you have stoichiometrically equal amounts of acid and base. In other words, where you've added an exactly equal amount of base into the acid. So essentially the amounts are exactly the same. Alright? And when that's the case, they neutralize each other completely, and with a strong acid and a strong base, that gives you a neutral solution, which would give you a pH of, everybody, it would give you a pH of 7. Alright? So for any strong acid, strong base titration, you'll always expect the equivalence point to be at pH 7. Alright? So as I said, initially the pH increases relatively slowly, and then it speeds up very high over this small volume range here, and then it slows down again to give you the top part of the S. Okay, that's for traditional strong acid, strong base titration curve. What I want to show you next is a similar thing, except where we have a weak acid, strong base titration. So let's assume we have the same strong base and we have a weak acid, let's say maybe acetic acid, for example. Alright. Couple of things that I want to show you. The general shape, as you can see, is exactly the same. It's that basic S shape. All right. You have the almost horizontal region here, as you did back here. You have the almost horizontal portion here that you had here, and then you have the almost vertical point in the middle that you had here. So they have the same general shape, but there are some differences. All right. One of the differences is what goes on right at the beginning here for a weak acid. Notice there is a little dip, so the pH increases kind of fast and then levels off. All right. Here, the pH increase was relatively steady when the acid was strong. There's something about when the acid is weak that initially causes the pH to increase fast, and then it sort of cools off for a while, and then it increases again. All right. And there's also something else important here. We have the equivalence point. Notice the equivalence point is not in the same place for a weak acid as it is for a strong acid. And then for some reason there is an importance about what's called the half equivalence point. And if you think, well, what's the half equivalence point? Well, if the equivalence point is where the amount of my acid, the amount of the acid that I've used is exactly the same as the amount of base that I've added in. Okay, so where I've added in the amount of base to neutralize essentially all of the acid, then the half equivalence point is the point where I've added in enough base to neutralize half of my acid. Okay, not all of it, but half of it. But for right now, I just want to focus on the shapes. Okay, the same basic S shape, but we've got that little piece right here. Now let's just talk a little bit about why there is this shape here. Obviously the pH is increasing here because you're adding in a base, as you would expect. All right. But let's just think about what happens when you add these two together. Weak acid and strong base. Well, it's a neutralization reaction, as you would expect for anything else. One of the products is H2O, because you're adding an acid and a base together. And then the other product is the conjugate base of this acid. In this case, it would be sodium acetate, NaC2, if I don't run out of room here, C2H3O2. Alright, if you prefer C2H3O2 minus, with that being Na+. This, of course, is the conjugate base of this guy. Alright, so if this is your acid, this is your conjugate base. Alright. So when you add in your strong base here, notice what you form. The strong base reacts with the acid to form the conjugate base of the acid. So what you're forming is a conjugate base of the acid that you originally started with. Let's see if anybody can remember. What do I have when I have a strong acid and I am forming some of the conjugate base of that acid? Well, what I'm forming is a buffer. Because I'm forming that buffer, you remember buffers can be pH resistant to a certain extent, pH change resistant, and that's why this pH change slows down for a little while. Eventually, though, the buffer gets overwhelmed and the pH increases in the same way as we saw before. But what's the importance of the half equivalence point? It does have a particular importance only for weak acid and strong base titrations, or weak base, strong acid titrations. It's not an issue for strong acid, strong base titrations. Let's say we had 25 mL of our weak acid, and we're adding in our NaOH. Now, let's assume the concentrations are the same. We'll just say they're 0.1 molar or something like that. The half equivalence point is where we've added in enough base to use up half the acid, so that will be essentially 12.5 mL of our NaOH. What that would do is, if you've used up half your acid, 25 mL of that acid would be a certain number of moles of acid, however many that would be. Okay. And when you add in the NaOH and you use up half those moles of acid, those moles that you originally had of the acid have been converted into the conjugate base. So let's say at the half equivalence point you have X moles of your acid. You have also produced X moles of the conjugate base of that acid. The important point being that the number of moles of each of these is exactly the same at the half equivalence point. If the number of moles of each is the same, the volume is constant for each of these, so therefore the concentration of these is also the same. Alright, so the concentration of our acid at the half equivalence point is going to be the same as the concentration of our conjugate base. Now, if you remember an equation called the Henderson-Hasselbalch equation, alright, which looks like this. So the pH of any buffer solution, because that's what we have here, so in this region we have a buffer solution, the pH of any buffer solution looks like this. And let's just apply what we've been talking about. The pH is equal to the pKa of whatever acid we're talking about, in this case acetic acid, which the pKa I think is, well, I forget what it is. I think, well anyway, it doesn't matter. pH is equal to the pKa plus the log of the base in the acid. At the half equivalence point, these two concentrations are equal to each other. So if that is equal to that, this whole thing becomes 1. Now what is the log of 1? Of course the log of 1 is 0. So what that means is, at the half equivalence point for a weak acid strong base titration, the pH of the solution is equal to the pKa of the acid. And that is an important thing to know. Alright, the pH of your solution at the half equivalence point is equal to the pKa of the acid. Only at that point. At no other point is that true. Okay, that's a little bit about weak acid strong base titration. And this is just a slide showing the two previous pH curves together, just to illustrate the difference in the initial part of the titration curve. Okay, that's the main reason you'll notice the difference. Also notice the equivalence point slap bang in the middle of the curve here. The equivalence point is further up above pH 7 here. Alright, and that's mainly because it's higher than pH 7 because you're adding in a strong base to a weak acid, so that equivalence point is going to be higher than 7. Now, there aren't scales on here, but one other thing to notice if there were scales on here would be, for a strong acid, that initial pH would be somewhere around 1. Probably. For a weak acid, again, the scale here doesn't really show that, but the initial pH would actually be higher because it's a weaker acid, so it might be something around 3 or 2.5 or something like that. Okay, so that's a little bit of a comparison of strong acid, strong base titration curves, weak acid, strong base titration curves. One other thing, polyprotic acid titrations. Polyprotic acid, of course, meaning an acid that has more than one hydrogen in it. Sulfuric acid would be one example of that. Carbonic acid would be another. Phosphoric acid would be yet another. Alright. If we go back to what we had here, our acid, in this case, is HCl. It has just one hydrogen to remove. Alright. And so we have this one vertical portion here that corresponds to that one hydrogen being removed from the HCl. Now for an acid with two hydrogens, then you should expect to see two of those. We've got region 1 here, region 2 here. If we had phosphoric acid, we see the same thing. It would carry on up here and so on. Okay. Again, we have the situation where we can talk about the pH being equal to the pKa. In this case, because polyprotic acids have more than one pKa value, you'd have this guy at this half equivalence point here, you'd have this guy at this half equivalence point here. equal to pH would be equal to pKa1 here, would be equal to pKa2 here. If we could do the same thing here, if this was phosphoric acid, we'd have the pH would be equal to pKa3, for example. But again, if we just look at the basic shape of this curve, notice that it's made up of the general S shape again. Alright, this is one S right here, this is another one here, and this is another one here. So anytime you have a polyprotic acid, you're essentially taking a standard titration curve and stacking it up against another one. Because if you were to take this and put another one on there, what you get would be the titration curve for a polyprotic acid, essentially. Alright, so that's a little bit about polyprotic acids, and that's it. Okay, the only other thing I'll say is, here we've talked about titrating bases into acids. If we were to talk about titrating acids into bases, then of course the pH would go down, and we'd see essentially exactly the opposite of what we see here. So for a strong acid being titrated into a strong base, the pH curve would look something like, well, okay, that's not very good, but let me just try that again. It would be essentially the opposite of this. So it would look something kind of like that. That still isn't very good, but it would look something sort of like that. That would be sharper there. Alright, okay, that's it. Thank you.